This podcast is going to have us look at percent yield, and you may not be familiar with the term percent yield, but I assure you, you have used percent yield every single time you calculate a grade on an exam. So let's look at how this applies to chemistry after we look at how it applies to cookies. Oh my gosh, these cookies look so good. I'm so hungry. Now we're going to have to get some cookies. I apologize, but I think chemistry sometimes is best taught through food, so bear with me and then go get some cookies. So let's say you have a recipe that makes 60 cookies. That's 5 dozen cookies. That's an incredibly large amount of cookies. If you're making them as big as I am, you're not going to get 5 dozen out of that. But for argument's sake, let's just say it makes 60 cookies. You're baking the cookies. You get distracted by something on your phone and an entire pan that's 12 cookies gets burned. So you only have 48 cookies that are edible. What is the percent yield of the cookies? Well, we would simply say, okay, I made 48, 60 cookies were possible. Okay, so you'd get a value of 0.0 or 0.80. That's not a percent. We multiply by 100. Your recipe yielded 80% cookies. You lost 12 of them. Your percent yield was 80%. That's not good enough for cookies, but that's really good if you were in lab and these were chemicals that you were trying to find. The example that I gave in the opening slide with an exam, say you, and I'm going to use really easy numbers, okay? So say you got a 75, you got 75 points out of a possible 100 points. Okay, multiply that by 100, you got a 75%. So your percent yield was 75% correct, 25% wrong. My percent yield for cookies, there were 80% that were edible, 20% that went in the trash. So percent yield is not a really difficult concept. So let's talk about what percent yield means when we talk about chemicals and chemistry. The percent yield in chemistry is the amount of product that is actually formed in a reaction. Believe it or not, you're not going to get 100% of the predicted amount of product in your reaction. You're going to get well below that unless you're an incredibly good chemist. Even the best chemists are going to get below that. So to calculate the percent yield, we'll take the theoretical yield and we're going to need the actual yield. Your theoretical yield is the amount of product expected from a given amount of reactant. Okay, so if I have a recipe that makes 60 cookies, I'm expected to get 60 cookies. In chemistry, we can base this on the coefficients of a balanced chemical equation. We would use stoichiometry to determine this. If I'm starting with this reactant, how much product can I form? Notice the change in substance means you have a mole ratio. That is all stoichiometry is. The actual yield is the amount of product obtained from a reaction. Think about the amount you actually get in real life or what's obtained through the experiment. As you know, I'm a visual girl, so let's look at some visuals. Your theoretical yield, you are using stoichiometry to determine. Maybe you start out with grams of a reactant and you want to find out how many grams of product are formed. Well, we're going to use a series of mole conversions and the stoich mole ratio in order to determine what to expect. Here's how much we should get if the conditions are perfect, and they never will be. Just don't even get your hopes up. And our actual yield is what we can measurably find in lab. That's the amount of product we can measure that we get at the end. And I will tell you right now, no matter what, you're going to get less than your theoretical, and you're just going to have to learn to be okay with it. We have toyed around with this prior to this slide, but the official calculation is going to be your actual yield. So this is what you measure in lab, or the amount you're given in a word problem, divided by your theoretical yield. So just to put this into the context of exams, this would be your score versus the total points possible. Now I have the units of grams here. You don't have to do grams. You could do milligrams and milligrams. So long as these are equal to each other unit-wise, they're in the same prefix, it doesn't matter what the unit is. Why we kept the unit in here was so that you could see that units cancel, leaving you with a percent at the end. So here are your steps to do percent yield. You're going to determine your actual yield. So this is going to come from your word problem, or you're going to measure this in lab. Then you're going to determine your theoretical yield. You'll start by using the given reactant amounts, and you'll convert this to what you expect to get in the products using stoichiometry and the mole ratio. That's where we change from one substance to the next using the coefficients from our balanced equation. Then we can plug those values into the percent yield calculation, and you're done. Why do I need to know anything about percent yield? I'm going to be a nurse. Let me tell you why it matters. Because in the pharmaceutical industry, yield is important, and you will be coming in contact with a ton of drugs. So maybe it's a little bit of a stretch as to why it's important to you, but let's work with it. So most of the drugs that we're administering to our patients are made in a lab. We're not just collecting them on the trail on a hike. You're going to need to make large quantities of these, and you're going to need to do so in a cost-effective and efficient way. So you don't want a lot of waste. You want your percent yield to be as close to 100% as possible, to maximize profits, to maximize time, and be most cost efficient. So the reactions that are used to make drugs such as albuterol, which is used for asthma attacks, it's an inhalant, they usually are going to take 5 or more steps, sometimes as much as 10 steps. So let's take a look at what that means in terms of our percent yield. So let's say you're really, really, really good, and each of your steps has a 90% yield. Okay, that's incredible. All of our chemistry students would love to have a yield remotely close to that. So let's say you're a really good chemist and you're getting 90% yield on every step to make your albuterol. Okay, if that's the case, okay, we're going to convert to decimals. So you just see me converting to decimals. You are going to wind up with 0.59 times 100, 59% for your yield. Wait a second. But every step had a 90% yield. No, when you multiply all this together, you're accounting for a loss. You're only making close to 60% of the possible, of the theoretical yield you should be able to make. That's pretty dang low. And now think about, what if this was a 10-step process? Wow, it would be even lower. And let's say, for example, you're having trouble with step 2. You can't get better than a 50% yield on step 2. Look at what that does to your percent yield overall. It drops it almost in half when you struggle with one of those steps. So percent yield is an incredibly important topic, and it's incredibly important when we have multi-step synthesis reactions, say in the pharmaceutical industry. All right, let's dig into a problem. This problem's worded a little bit funny. It doesn't give us a lot, but let's see what we can get from it. So it tells us that we are reacting 1.73 grams of calcium with excess oxygen. Okay, here we're seeing calcium reacted with oxygen, perfect. And they're telling us also that we produce 2.01 grams. Okay, so they're telling us what we produced. Because they're telling us what we produced, it's coming from the word problem. I know that this is the actual yield when we start with 1.73 grams. They want to know what the percent yield is. And as a friendly reminder, for the percent yield, we're going to take the We're going to take the actual yield over the theoretical, and we'll multiply it by 100. So I have the actual, but I don't have the theoretical. However, because I know how much we're starting with, 1.73 grams of calcium, I can find the theoretical yield using stoichiometry. All right. So we know we're going to start with grams of calcium, and we know we want to figure out how many grams of calcium oxide could, in theory, be produced. Okay, so that's what we're, in theory, going to produce. We know what was actually produced, but we have to figure out, based on the mole ratios, what we could produce. So we're going from grams of one substance to grams of another. That should be a red flag that somewhere in the middle we're going to have a mole ratio. That's the stoichiometry. We're going to switch from calcium to calcium oxide. Well, you can't use a mole ratio if your units aren't in moles. So our first step is going to be to convert grams of calcium to moles of calcium. And I'm going to do this using the molar mass of 1 calcium. Looking at my periodic table, that's 40.08 grams of calcium per mole of calcium. There's a conversion factor. Our mole ratio should give us moles of calcium oxide. I don't want moles of calcium oxide. I'm going to have to convert that to grams of calcium oxide. And I'm going to do that by adding up the mass of 1 calcium and the mass of 1 oxygen to get the molar mass. The molar mass for calcium oxide is 56.08 grams per mole. We have everything we need in order to set up this problem. So let's do a T-chart so we can figure out the theoretical yield. So 1.73 grams of calcium, the first step is to convert that to moles. So looking at my conversion factor, I actually have to flip that. I want the grams on the bottom to cancel the grams of calcium. Now we have moles of calcium. We are here. We are ready for our mole ratio. Looking at our balanced equation, we have 2 moles of calcium. I'm grabbing that straight from the coefficient per 2 moles of calcium oxide. Mathematically, this doesn't do jack squat. Times 2, divide by 2. However, you have to show that we've canceled units and substances for one substance, and we've converted that to the next. So this is very important to show that you've done that work. Now we're in moles. We are going to use the molar mass of calcium oxide to convert to grams. So we know that 1 mole of calcium oxide is equivalent to 56.08 grams of calcium oxide. We are left with grams. We want grams of calcium oxide because I can then take this. This becomes my theoretical yield. Multiplying across the top, multiplying across the bottom, and then dividing the value on the top by the value on the bottom, you are going to get 2.42 grams of calcium oxide. I'm using 3 sig figs because that's what my problem used. So this is my theoretical. Finishing up our problem, we are going to take our actual yield, 2.01 grams over the theoretical 2.42 grams. Multiply by 100, and what does that give me? 83.1% yield. That's pretty darn good.